All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Small crowd today. All good. All right. So today we're going to be talking about kind of the specific parts of the body. So on Tuesday, what we did was we reviewed a little bit of mechanics, and so we reviewed, what forces are, what moments are, how to draw a free body diagram, how to analyze that stuff. And so today we're actually going to put it into practice. And so over the next 2 weeks, you'll see that we're going to be kind of working our way. Well, we're going to start with the upper extremity, and then which is your arms and your shoulders, and then we're going to go to your legs, and then we're going to look at your spine after that. Okay. And so what you'll see is kind of, during this time, we're going to be practicing all this, what I call static biomechanical analysis. But also what I'm hoping for is that over these next couple weeks, you'll also start to learn more about, what the different parts of your body are, and how they're designed. And so, the different parts of your body, the bones and the muscles, they have different, sizes, different shapes, and they all have an important purpose, based on the roles that they're expected to serve. And so, we'll start with the upper extremity today and just kind of work our way around the body from there. Okay. All right. And so another announcement I want to make, starting tomorrow, I will be unavailable because I am going to my high school friend's wedding. And so I'm one of his groomsmen. And so we have an entire weekend planned. And so I will be going down to Temecula and getting absolutely shit-faced for my friend's wedding. So if you're interested, Monday, which is a brilliant idea by me to have Monday, 9 o'clock a.m. office hours. And so if you want to check and to see if I'm still alive, and if I am not hungover like crazy, then you can stop by office hours on Monday, just make sure I'm okay. And so, so that's happening this weekend. And so normally if, normally I get, a handful of emails on Friday nights, Saturdays, and I try to get back to you by Sundays. This weekend, I will physically not be able to do that. And so, don't expect any responses from me until Monday morning. Okay. But I don't think we have any homework to do. And so, I think for this class, I think we'll be okay. All right. And so are there any questions I can answer before we get started for today? No? Okay. All right. So let's go ahead and get started. And so the title or the topic for this, for this lecture and probably the next one is going to be upper extremity biomechanics. Okay. So let's introduce it first. And so, up to this point, like I mentioned, we've talked about, kind of what I consider to be the biology of this class. And so we talked about, the structure of bones, what they're made of, the structure of the muscles, how they work, and the joints, right? And so, all the different tissues in the body. And we've gone over kind of just, we've just kind of reviewed how mechanics work in general, okay? And so now, and I know kind of the first part of this class just necessarily has to be a little bit slow, just because, for a lot of people, it's their first time seeing biology in a while. And so, I want to make sure we do all that. But now, hopefully things in the class will start to pick up and get a bit more interesting, okay? And so the way that this is going to be structured is that we're going to take, a more careful look at each of the different parts of the body, okay? starting with your arms and your shoulders. And so, we'll introduce all the different bones and muscles and the joints in your arms and shoulders today. We'll do some example problems of, how you can compute things like muscle forces, the joint reaction forces in your upper extremity. And then we'll close probably next Tuesday talking about, what are some of the more common injuries that can happen in the arms and shoulders and how they occur, okay? All right, and so like I mentioned, we're starting with the upper extremity, and what's unique about these body parts is that they're responsible for, what I consider how we interact with the world. So, how we handle objects, when we see a new object, when a baby sees an object, the first thing they do is they try to reach for it and pick it up with their hand, right? Because, we're very tactile species, so we like to kind of reach out, we like to touch stuff, we like to see how it feels. And the way that we interact with the world is through our arms and shoulders. Okay, and so let's talk about general characteristics of the upper extremity. And so when you compare, the bones and the muscles of your arms and shoulder compared to, say, your legs and your spine, you'll notice that the bones and muscles for your upper extremity are a lot smaller than those of the other parts of the body. Okay, and the reason for this is that they're not really designed for load bearing. And so, when you're standing up, even, when you're sitting down, the parts of your body that handle your weight are your legs, your back, and your spine, right? But you're not really in situations of lot where your arms have to handle, your body weight. And so, for those reasons, there really isn't any practical reason for you to have, very large arm bones and very large arm muscles. Okay. And so, you'll see that, most of the tissues in there, upper extremity, are quite small. Okay? But in comparison, the upper extremity is capable of a much wider range of motion and control. And control there being kind of the finer point. And so you can control, the amount of control that you have in your hands and your fingers is much more fine than you have with your feet, right? For instance. And so, I think what a lot of people are doing right now is you're writing notes on your piece of paper, right? You do that with your hands. And so we take it for granted because writing is something that we do almost every day in our lives, but writing is actually a very, very sophisticated and complicated, movement. And so you have to make very, very fine strokes with your hand, and it has to be very coordinated in order for you to draw neatly. Compare that to try writing your name on a piece of paper with your feet, and I think you'll find that you're not very successful. And so, I think that in itself is a great example of what the upper extremity is capable of. It's capable of these very fine movements that no other part of your body can do. Okay. And this is granted by just the amount of control you have over the muscles, and just the wide range of motion that you can have with your upper extremity as well. Okay. And we talked about the shoulder joint, briefly. We know that the shoulder joint is very loose. But part of that allows you to do a huge range of motion with your shoulder that you can't do with any other part of your body. Okay. All right, so let's take a look at the bones of the upper extremity. And so, here's kind of the anatomy portion of this. And so, there are a lot of bones actually that are involved in your hand, but we're just going to focus on kind of the main ones here. All right, and so we're going to start kind of near the center of your body, so kind of near your rib cage, and then kind of work our way towards the fingers. And so the first bone that's important is your clavicle. And what's interesting about the clavicle is that it's one of the few bones in your body that you can actually feel, just with your fingers from the outside of your skin. And so if you put your hand on your, I think normally people call your collarbone. And so your collarbone is the one that kind of sticks out the most. Okay? It's also one of the most common bones that are fractured because it's so exposed. And so most of your bones have kind of a thick layer of either fat or muscle or both that protect it from kind of outside outside impacts. Your clavicle is just kind of sitting out there. So the only thing that's really protecting your clavicle is just a thin layer of skin. And so if you get struck on your collarbone, more likely than not, you're probably going to get a fracture because there's really nothing there protecting it. And it's quite thin too. So compared to other bones, it's a very thin bone. So protecting your collarbone, protecting your clavicle is something that's important, especially if you're doing something like impact sports. Next, you have your scapula. And so this is known as your shoulder blade. And so it's kind of like a triangular, it's kind of hard to see in this picture here, but the scapula is kind of like, it's like almost like a triangular bone kind of in the back right here. Okay. And so it really looks like kind of a thin sheet of bone. So that's why we call it the shoulder blade. Okay. And kind of the most defining feature of the scapula is actually this kind of spherical cavity that it has, at the end here, which is where the arm bone, the upper arm bone attaches. Okay? And that cavity is called the glenoid cavity, glenoid fossa. Okay? All right. And so speaking of the arm bone, we have the humerus, which is the upper arm bone. Okay. And so this is the long singular bone for the upper arm. And so it's quite thick because it is just one of them, right? And so this is kind of your upper extremity version of your thigh bone. So it's not nearly as thick as a thigh bone, but it kind of serves that purpose. And this one's a bit thicker than the other ones because there's quite a few muscles that actually attach to this bone. And so it has to be a bit stronger than the other ones. Your lower arm is comprised of two bones, which are called your radius and your ulna. And so the two bones are shown right here. So your radius kind of both bones kind of have the same structure. So they kind of have a thin end and a thicker end, but each of them are kind of rotated 180 degrees relative to each other. So the radius has this thicker end near the wrist, and so it makes much bigger contact with the wrist, whereas the ulna has this thicker end near the elbow. Okay. And so what we say typically is that the radius kind of forms the joint with your hand bones and the wrist joint, whereas your ulna kind of forms the joint at your elbow. Okay. And the ulna is a little bit bigger, but not by too much. All right. And so those are the two bones in your, in your lower arm. Next, we have the carpals. Okay? And so the carpals are, it's just a general term for all the bones in your hand. And so if you actually look at your hand bones, you can see there's quite a few of them over here. And this picture doesn't even show all of them. And so there's a lot of other smaller ones on the other side. But typically we call those the carpal. In total, we call those the carpal bones. And then connected to the carpal bones are your metacarpals. And so those are kind of the bones at the base of your fingers. Okay? So all of these bones right here are your metacarpals. Okay? And so those are the bones at the base of your fingers. And then the bones at the ends of your fingers are known as your phalanges. So these bones over here are your phalanges. Okay? All right. And so, I wanted to bring this up, and we'll take a look at the muscles on the next page too. And so, I wanted to bring these up just because, we are taking a careful look at the biomechanics of the upper extremity. And so, you should know, you should at least be exposed to all the different names of the bones and muscles there. But again, this is not something I expect you guys to memorize. This is not just a biology class. And so I'm having this here mostly just as reference. And so, if I do speak about them, or if you do read about these particular bones in the textbook or in other places, then you'll kind of have this figure here, and you'll have these notes where you can refer back to know kind of exactly what people are talking about these bones. Okay. Where did my annotations go? All right. Okay. Any questions on the bone structure of the upper extremity? All right. Okay, so now we have the muscles, and so here are the main muscles of the upper extremity. And so this will include a couple muscles in your back as well, just because their primary action is to move your arm. Okay. And so once again, we'll start kind of near the top, and we'll kind of work our way down. And so the first muscle that we have here is the deltoid muscle, and so that's commonly referred to as your shoulder muscle. Okay, and so that's kind of the muscle that's kind of on the exterior of your shoulder. And so it kind of all runs kind of right there. Okay. And so you can feel your deltoid muscle. So if you kind of feel the outside of your shoulder, that's basically your deltoid right there. Okay. And so what the deltoid muscle is responsible for is abduction of your arm. So if you've ever done shoulder workouts where you kind of did shoulder or arm raises like this, that's your deltoid muscle working out. Okay. All right, next we have the pectoralis, which is your chest muscles. And so I think everyone's heard the term pecs before. And so pecs are short for pectoralis. Okay? And so that's kind of the big muscle that's on your chest. And that's mostly responsible for kind of pushing your arms outwards and rotating them out. Okay? And so, I think the most popular exercise, that people think of when they think of going to the gym is, bench pressing. And so that primarily works out your pectoralis muscle. Okay. Next, we have the latissimus dorsi, and so which is not pictured here. And so the latissimus dorsi is kind of, this muscle kind of right here. So it kind of forms a little bit of a triangle kind of in the back, right? And so it's not shown because it's in the back. And so that muscle, it also helps support your spine, but it also can rotate your arm as well. Okay, so that's another important muscle. All right, and so now I think we get to the muscles that are actually in the arm. So first we have the biceps brachii, what I call the Popeye's muscle, and so that's the muscle that Popeye the sailor likes to flex. Okay, and so that's responsible for elbow flexion. And then you have the brachialis muscle as well. And so the brachialis muscle it's not shown much because it's kind of here and it kind of runs underneath the biceps brachii, but it's also helps with elbow flexion. Okay. All right. Next we have the brachioradialis, which is kind of barely shown in this figure right here. So let me kind of erase everything. And so your brachioradialis is your forearm muscle. Okay. And so that's the main muscle that you feel kind of when you touch your forearm. And that's used for kind of flexion at your wrist. And so it kind of helps close your hand. Okay. And then finally, we have the triceps muscle, which is on the backside of your arm. And that's responsible for elbow flexion. Okay. right? So that's the triceps right there. Yeah. And so both of these figures, I couldn't get every single muscle on here, but then I think these two figures combined kind of show most of the muscles that are important for the upper extremity. All right. Any questions on this? Yeah. Or say again? So the pectoralis is actually a collection of muscles. And so they're the major muscles. You'll see major muscles and minor muscles. And so major muscles are just usually the bigger ones, and the minor ones are smaller. And so if you kind of really break it down, each of those individual muscles are responsible for different types of movement. But in totality, we can kind of combine them together as the whole pectoralis muscle group. Yeah, you have several muscle groups like that in your body. So like your quadriceps muscle in your thigh, that's actually a combination of 4 different muscles in the front of your thigh. They all do very slightly different things, but they all kind of combine together to do knee extension. So your pectoralis is another example of that. Question: what is my favorite exercise, biceps or triceps? Well, I mean, they're both important. It's not good to favor one over the other one, but and I can't really say because I haven't really seriously worked out in quite a few years, and so I will say undecided. I need to get into better cardio shape before I do any muscle training. I think that's the real answer for that. Oh, nice. Yep, that's true. Triceps are much more volume. Any other questions on this? Okay, so we went over the bones of the upper extremity and the muscles. So let's go over the joints. Okay, so you have kind of three main joints that I think people are mostly concerned about, and then you have the joints of your fingers as well. Okay? And so the 3 main joints are your shoulder joint, the elbow joint, and the wrist joint. Okay. And so what I've done for these joints is I've called them, I've named them based on their more, I would say, colloquial names. And so what people usually refer to them when they're talking about these things. But I've also included their scientific names as well. And what you'll notice from the scientific names is that they're made up of the bones that, comprise that joint. Okay? So for example, the shoulder joint is sometimes called the Humeroscapular Joint. And the reason for that is because it's the joint between the humerus being the upper bone, the bone in your upper arm, and your scapula, which is your shoulder blade bone. Okay, and so hence the name humeroscapular. Right. Okay, so the shoulder joint is a ball and socket joint, and so it's it allows for a lot of range of motion, but because it's so flexible, it's also subject to a lot of dislocations as well. And so we've already talked about that before. Your elbow joint is primarily a hinge joint, and that's formed between the humerus of the upper arm and the ulna of the lower arm. Okay? It allows your elbow to flex and extend. And you have your wrist joint, and so it's primarily a hinge joint, but you can also kind of rotate it around a bit. Okay? And so that's formed between the radius and the hand bones. And then you have the various joints within your hand as well. So your hand is actually quite complex because there's a lot of different joints. And so there's the wrist, and there's a joint between each of your individual fingers and the hand. And then within the fingers too, each of them have multiple joints as well. And so, the hand is complex and it allows for quite fine control, but that's what allows it to do so many cool things. Okay. And opposable thumbs. And so, opposable thumbs is something that's quite unique to humans, and it's basically what's allowed it. It's basically what has allowed us to take over the world compared to tigers and lions, stuff like that, which don't have opposable thumbs. I'm reminded of this every day because my wife and I, we just recently got a kitten, and so she likes to try to grab things, but she doesn't have thumbs, and so when she tries to grab things, she kind of tries to like clap at it, and I just think it's the funniest thing in the world. It's like, man, evolution really shit on you, huh? We're the ones that got opposable thumbs. All right, any questions on this? Okay, and so, that was a very kind of quick overview of the bones, the muscles, and joints. And so I wanted to bring those up because those are the main kind of tissues that we went over earlier in the class. Okay? Now we're going to start to get into the calculations. And so we're going to start by doing static biomechanical analysis. Okay? And so if you remember the example that we did at the end of class on Tuesday, where we drew the free body diagram for that rod, and we used that to solve for some unknown forces, we're basically been doing the exact same thing here. Okay. And so, when we perform static biomechanical analysis, our goals, or what we're looking to solve for most of the time, are going to be muscle forces and joint reaction forces. Okay. And so what we're going to be analyzing is we're going to be analyzing the upper extremity under certain conditions. So under cases where they're supporting a load or they're pushing against something. Okay. And what we're interested in is, under these conditions, what are the muscle forces and what are the joint reaction forces that are necessary to produce this situation. Okay. Okay. Because the body needs to exert some force in order to do this. Okay. All right, and so with that, I'm going to go ahead and switch to my iPad, and I have I think 4 examples that we can do, and I'm going to try to get through as many as I can. Okay, but that's basically the idea. And so it's kind of a fancy name, static biomechanical analysis, but all it really is just we're drawing free body diagrams, we're forming the equations of motion, and we're solving for some forces basically. And so, if you recall kind of from the beginning of class, I said that, biomechanics, there's nothing really that special about it. It's really just mechanics, just with a biology flavor. And so you'll see that here. And so, we'll be talking about things like guys doing a dumbbell curl or supporting a weight with their shoulder. And so these are obviously real, situations, but when you kind of extract out the free body diagram, it really is just mechanics. And so, I want to emphasize that because I don't want it to be anything that's kind of scary or foreign to you, because I think you guys have all done this at this point. Okay, all right, so let me go ahead and stop sharing here and share from my iPad. Okay. And so let's do some upper extremity. Static. And so just as a reminder, we're going to be analyzing static situations. And so there's going to be no movement. Static situations of the human body, and what we're interested in is computing muscle forces and joint reaction forces. Okay. All right, so let's just jump right in. So let's start with a very simple example. So let's consider a situation of someone kind of holding a weight in their arm, or in their hand, I should say. All right, so let me do my best here. So let's say that this is the person's arm carrying a box. And what we're interested in here is the bones of the lower arm. So the radius and the ulna. And so I'm just going to go ahead and lump them together into one bar. So this bar right here represents the radius and ulna. So of course, the weight here is going to be applying a downward force. We're also going to consider the weight of the arm itself. Okay. So this WA here, this is the weight of the lower arm. Okay. And this joint right here I drew, this is your elbow joint. And we'll consider the action of a single force. And so we'll consider a single force going upwards like this. Okay. This FM here, this is, it could be any of the elbow flexor muscles. And so we'll say this is the biceps brachii. Okay. And just for simplicity in this problem, we'll assume that the biceps brachii are going to apply a force that is perfectly vertically upwards. Okay. So this is a 90-degree angle. All right. And so what's happening here is that, if we consider everything relative to the elbow joint, we have the weight W and the weight of the arm. They're going to be trying to do the same thing. And so they're going to be trying to rotate your lower arm clockwise in this case. Okay. And so the only thing that's opposing that is the force from the biceps brachii. Okay. So that's kind of what's going on just from a writing perspective. All right, and so another thing that we're going to have here is that at the elbow joint itself, we're going to have a reaction forces. Okay. So we'll say it's Rx, Ry. Okay. And so reaction forces Rx and Ry are going to form at the joint. And their main purpose is to ensure this entire system is at static equilibrium, because we're going to assume that everything here is static. Because probably what we'll find is that the muscle force just kind of based on how far it's acting from the elbow joint. It's not going to perfectly cancel out the two weights just by itself. It's going to prevent the rotation, but in order to prevent any of the linear motion, Fx, Fy, we're probably going to need some reaction forces as well. Okay. And so in this problem, what our goal is, we're going to have three unknowns. And so we're going to assume that the muscle force is unknown, as well as the joint reaction forces. Okay. And so we're going to compute those forces from this problem. And so just like we did at the end of class on Tuesday, we're going to draw the free body diagram, and then we're going to write out the equations of motion. And then those three equations of motion will allow us to solve for, our three unknowns. All right, any questions on this? Okay. All right, so let's go ahead and get started. So let's start with a free body diagram. I'm only drawing it because I forgot to label everything in the picture, but it's okay. And so what we have here is a rod. Okay. We have a fixed, well, a pin support here. Okay, so our rod here is going to be pinned at the elbow. And then we have three forces. And so the first force that we have is the weight of the object. Okay, so that has a weight of W. Then we have the weight of the arm itself, W sub A. Okay, so both of those, because they're weights, they're going to be acting in the downward direction. We don't have values for these yet, and so and there's a reason for that. I want to analyze some of the equations that come out, but at the very end, I'll give you some typical numbers, and then you can plug in and solve for these. Okay. And then we have the force, the muscle force FM, pointing upwards like that. Okay. All right, so those are all the forces. But we also need to know a bit more information. And so just for the moment's sake, we also need to know the moment arms. Okay. And so, relative to the elbow joint, we're going to assume that FM is acting at a length of LM away from the elbow joint. The distance between the elbow joint and the weight of the arm, WA, is going to be L sub A. And then the length between the elbow joint and the weight of the object is going to be L W. Okay. And so those distances, are going to be primarily used in the moment equation so that we can sum up their moments around the elbow joint. Okay. So now we're going to write out the equations of motion. And so we're going to sum up the forces in the X, the Y, and X and Y directions, as well as the moments around the elbow joint. Okay, so we'll start with the forces. Oh, I forgot to draw on the reaction forces. And so at the elbow joint, we're going to have Rx. Assume Ry is going in the vertical direction. Right, so don't forget to draw in your reaction forces into your free body diagram, because that's important too. Okay, so we sum up the forces in the X direction. And so here we have a very simple case. We actually have only one force in the X direction, which is Rx. And we set this equal to 0 because this is a static case. And so there's no motion. Okay. Okay. Now we sum up the forces in the Y direction. And so we have 4 of these forces. And so we have R sub Y positive, then we have F sub M positive, a minus WA, and a minus W. Okay. And that's equal to 0. And so those right there are our first 2 equations. Okay. And so the first one's actually really useful. And so from the first equation, we can see that the reaction force in the X direction is 0. Okay. And so this solves for one of our unknowns. So we know that Rx is equal to 0. Okay. That's good. Which makes sense because all the other forces in this figure here are all vertical forces. And so it wouldn't make sense to have a horizontal reaction force. There's nothing for it to react to. All right, and so now we have the sum of the forces in the y direction. And so we have r sub y, which is an unknown, f sub m, which is unknown, and then w, a, and w, we're going to assume that we know these. Okay. Right, and so we have two unknowns in this equation, but only one equation. And so we're going to need one more equation. And so to get that last equation, we're going to need to sum up the moments around one of the joints. And so the joint that we're going to select in this case is the elbow because Rx and Ry are there. Okay. And so remember what I mentioned on Tuesday. So when you're summing up the moments, you have the freedom to choose where you want to sum up the moments around. So where you want your joint to be. And so usually it's a good idea to sum your moments at a place where things are going to cancel out. Okay. In this case, it's kind of obvious because all the distances we're given are, based on the elbow joint, and so it makes sense that we sum up the forces there, or sum up the moments there, but that's something that you can kind of choose based on what's going to be easiest in the problem. All right, so let's go ahead and do that. And so if we sum up the moments around the elbow joint, what we get is we have Fm times its moment arm, which is Lm. Okay. And since this, since this force right here is going to try to rotate the lower arm counterclockwise, then we give it a positive sign. Next, we have the moment from the weight of the arm, and so that's WALA, okay? And that's negative because that force would try to rotate the arm in the clockwise direction. And then we have the moment from the weight of the object, and so that's WLW. And so we sum all these up, they're equal to 0. And so let's look and see what's unknown in this equation. So we know the weight of the arm, we know the weight of the object. Okay, those will usually be given to you in the problem. Okay. And so, we'll assume that we know all the lengths as well. Okay. And so the only thing that's unknown here is Fm, but this works out really well because we only have one unknown in this equation. And so we can use this equation to solve for that unknown. So let me go ahead and move the WA, LA, WLW to the other side. So FM, LM is equal to WA, LA plus WLW. Okay. And so I just took these two terms and moved them to the other side of the equation. All we have to do here is divide by LM. And then we get our solution for FM. And so the muscle force is equal to WALA, and so that's the weight of the arm times its moment arm, and then WLW, which is the weight of the object times its moment arm, divided by LM. Okay. Any questions on how we obtain this result here? All right, so I want to pause here for a second, because I want to examine this result, because, even though this is a fairly simple example, there's a lot of conclusions we can draw from this result here that are, I think, generally applicable to most, to most kind of muscle situations. Okay. All right. And so the way I'm going to do this is I'm going to look at everything in the numerator and then the denominator. Okay, so let's look at the numerator first. And so in the numerator, we have things like the weight of the object, the moment arm of the object, and the weight of the arm itself. Okay? So what's one thing that everything in the numerator here has in common is that when the values of those parameters in the numerator go up, then FM is also going to go up as well. Okay? So that makes a lot of sense, right? And so if you compare, holding up, something like an expo marker, right? So your arm doesn't have to work very hard to flex that expo marker. But if you hold something heavy, like a bucket of water, that's going to require a lot more work. And so, it makes sense that your arm muscle has to work harder when you hold heavier objects. And so, you didn't really need an equation to tell you that, but there's the mathematical formula for that. Okay. And another interesting thing too is that the longer your arm is, LA and LW, the longer your arm is, your arm will have to work harder as well, because that's kind of more of a larger moment arm that they have to account for as well. And so, generally speaking, people with kind of larger bodies, longer limbs and things like that, their muscles have to work a lot harder for them to do kind of the same things as smaller people do. And so that's kind of the reason why, if you kind of follow Olympic sports, much at all, if you look at like very high level gymnastics athletes, a lot of them are quite short. That's because, they can do all these very sophisticated, very athletic, gymnastics moves with a lot less work and a lot less energy, because their body is just naturally just a lot more compact. Okay, so let's look at the denominator, because I think this one is the more interesting. So in the denominator, we have LM right here. Okay? We only have one parameter in the denominator. And so LM is the attachment point, or the distance between where the muscle attaches and the respective joint. Okay? Okay. Otherwise known as the moment arm of the muscle. Oh, thank you. All right, question. So does that mean people with smaller statures can build muscle faster, easier than people with larger statures? So I would say that their workouts are probably a little bit less efficient, because when they're doing some kind of workouts, then their muscles don't have to work as hard to do to produce kind of the same motions, right? But at the same time, they just have a lot smaller mass as well. And so, as that muscle kind of builds more and more mass, it's going to show up a lot more visibly on smaller people than larger people. Yeah. But they're a lot more limited. And so, because their muscles are kind of a lot smaller, then they can't start out with a very large weight when they're doing certain exercises. And so, you're kind of starting out at different places, but they how much they grow kind of depends on a lot of different factors. Yeah. But I would say that if you're for two people that kind of do an equally intense exercise regimen, and so same number of reps, same weights and stuff like that, you're definitely going to visibly see it on the smaller person faster, just because they have smaller mass and smaller lengths. Yeah. All right. And so the moment arm of the muscle here is in the denominator. So, whenever you have something in the denominator, you know that it kind of has the inverse relationship. And so as LM gets smaller, then FM gets bigger. Okay? Okay? And so the smaller your moment arm, the more your muscles have to work in order to produce the same kind of motion. Okay, and you'll see in a bit that that I think it's kind of surprising to people that when you hold a certain amount of weight like in your hand, maybe say something light like 10 pounds, your muscle actually has to exert much more force than that to actually lift that up because the moment arm is a lot smaller. Okay, and so typically muscle moment arms are quite small. And so because the muscle moment arms are smaller, then the muscle has to work much harder than the weight would indicate, right? And so let's say that you're just holding like a 5-pound weight in your arm, right? You'd be surprised to see that your arm muscles, we're doing a simple example here, which is one muscle, but in reality, usually it's multiple muscles working together. Those multiple muscles, if you add up all their forces, it's actually going to be, probably somewhere close to, maybe like 40, maybe 35, 40 pounds just to hold that 5-pound weight because the muscle moment arms, because they're so much smaller, to prevent that rotation, they have to pull just so much harder than those ones. Okay? And so typical values for the muscle moment arms will range anywhere between 2 centimeters and 6 centimeters in the body, okay, depending on which part of the body that you're looking at. But if you compare that, to the length of your arm, the length of your arm is a lot longer than just 2 or 6 centimeters. Okay. And so I think, this is something that I think kind of consistently surprises people as we kind of go through the next couple of weeks, is that, you're getting muscle forces that are like, a couple hundred pounds, just to do something as simple as just standing up, and it's surprising to people. But that's a consequence of having the smaller moment. And so you may ask, why is it that the human body is designed this way? Why is it that we have such small moment arms that force our muscles to work just so much harder? Because when you look at it just from a pure, just pure amount of work perspective, right? It seems to not make much sense. And so, you're just doing kind of very, average everyday activities, but your muscles have to exert just so much force just to do those activities. Okay? Because their muscles are designed to be compact. Right? And so, one reason first is to make sure that the form factor of the human body is relatively small. Okay. And so for this example, for your arm, your biceps brachii kind of attaches to your lower arm, very, very close. And so, it's even kind of hard to visualize just from the outside. But if your biceps, instead, to produce the same elbow flexing motion, let me go ahead and draw a picture for you. Okay. And so let's say this is your arm right here. So right now, your biceps brachii kind of attaches right here, right? With kind of a small distance between, the biceps brachii and the elbow, right? And so that kind of, makes it so that you have a smaller form factor, but think of the alternative. And so, if you really wanted to reduce the amount of force that the muscle had to do, your biceps muscle would actually attach closer to your wrist, right? And so that this distance right here would be much bigger. Right, and so that would result in a larger LM. And so let me go ahead and write out the equation here again. And so FM is equal to WA LA plus WLW divided by LM. Okay. And so if you increase LM in this case, and this is kind of the extreme case where you kind of extend LM as much as you can, then FM would be much smaller here, right? And that's true, right? And so the arm muscle wouldn't have to produce as much force. Okay. But if you had muscles that kind of attach all the way to your wrist, that would make the form factor of the human body, it would make you kind of much bigger, much wider than you are right now. Okay. And so, kind of we've evolved in a way that kind of encourages us to have kind of as small a form factor as possible. So so you can imagine, maybe our, deep ancestors, they had to maybe hide away from predators and things like that. That's kind of hard to do when you have kind of like this big bulging muscle that attaches to your wrist, like that. And so, having a smaller form factor is generally good for a lot of animals. Right. So that's one reason. But I think the more important reason is that it allows for, when you have smaller moment arms, to survive. When you have kind of smaller moment arms, it actually allows you to have faster movement of your limbs. Okay. And I'll again kind of draw two examples here for you. Okay? And so imagine like a drawbridge. Okay, so you have a bridge like this. Okay, and we'll do two examples. And so we'll do one example where the drawbridge is pulled up from its end. A little bit better. And another instance where the drawbridges will be pulled up kind of near, near the left side. Okay? And so the hinge for the drawbridge will be here on the left side. Okay. So on and so forth. All right. And so the goal for this bridge is for it to rotate upwards such that the drawbridge is vertical. Okay? And you want to do this in the shortest amount of time possible, without really worrying how much force you're going to pull. Okay? So imagine you have like 20 really strong dudes pulling on this. And so the amount of force isn't the issue. You just want to make sure that you get it done as quickly as possible. Okay. All right. And so the question is, between these two, which one is going to be able to pull up the drawbridge faster? Okay. right? And so between these two, the one on the right is going to be able to pull it up faster. Okay? And the reason for that is actually quite simple. And so the reason for that is that, when you attach right here, okay, as you can imagine, to pull this up, this point right here where the bridge attaches to has to kind of travel this distance right here. Okay. And so it kind of has to move from here to its final position where the bridge is kind of pulled up like this. Okay. If you compare that to the path that this point has to take, and so the one on the left, in order to pull all the way up, this point has to travel all this distance right here, right? So those points are significant because that's the point where you're kind of pulling on. That's the point where you're actually, that actually has to travel distance. Okay? And so the one on the left, there's just so much more distance to cover there. And so this is going to take longer than the one on the right. The one on the right is going to require more force because the moment arm here is much smaller. Okay, and so all of your all your villagers or knights or whatever, they're going to have to pull a lot harder. But when they pull harder, they can pull up the bridge much faster than the left side. Okay. And so if you look at this from kind of an evolution standpoint, faster limb movement is, much more highly valued. And so you can imagine, faster limb movement will mean that you're able to run faster, you'll be able to react to things faster, you'll be able to, just do kind of everything faster. So, that is much more valued than the amount of muscle force. And so, the kind of the point of all this was kind of, a long detour. And so, you'll see that when we put numbers in, the muscle force that your muscles are generating are going to be quite high, but that's by design. And so it allows you to do, a lot of the things that you can do as a human. Okay. Any questions on this? Okay. All right. And so that's the muscle force. Right? And so that's the formula for the muscle force there. And so we're not quite done yet, although we just have one more step. And so we're going to use that muscle force to solve for the vertical reaction force. So we're going to solve for Ry. And so the Ry, the way we're going to solve for it is from the sum of the forces in the y direction. Okay? And so what we get is Ry is equal to W plus WA minus FM. Okay. And so let's go ahead and plug in our value for FM. And so FM is WA LA plus WLW divided by LM. Okay. And so that's the reaction force at the elbow joint. And so let's go ahead and put some numbers on this, some typical numbers. Okay. And so we plug in some numbers for this. Let's say that the weight of the arm is 20 newtons. We are carrying an object that weighs 80 newtons. Okay. We'll say that LM is 4 centimeters. LA is 15 centimeters. LW, we'll say that's 35 centimeters. Okay. And so we plug all those things in, we get FM is equal to 775 newtons. Y is a negative 675 newtons. Okay. And so Ry, of course, is pointed in the negative direction. Okay. Right. And so you can see here that, you know, even though the arm itself, the combined weight of the arm and the object is only 100 newtons, the muscle force that's required to lift this is, you know, almost 8 times as high as elbows. Okay. And that's a result of the lower moment arm of the muscle force. Any questions on any of this? Okay. All right. And so that's the first example. And so, you know, that was kind of I know we spent quite a while talking about that one. But that in that case, we only considered a single muscle. Okay. In reality, you know, for most actions that your body could do, you know, you have kind of multiple muscles that kind of help supporting in that action. Okay. And this is kind of just for safety purposes. So, you know, it doesn't make, you know, it doesn't make a lot of sense to have just one muscle relied upon for a certain action, because then if that muscle breaks down, then you're kind of screwed. And so it's always good to have some redundancy in your system. And the human body is no different than that. Okay. And so let's do an example where we compute multiple muscle forces. And you'll see that we have to do something a little bit special. All right, and so let's do the same elbow joint as before, but now let's introduce some of the other arm muscles. Okay. So let's say that's your upper arm, that's your lower arm, that's your hand. Okay. So same as before, we're going to have a weight here that we're carrying in our hand. We have the weight of the arm as well. But let's consider 3 different arm muscles. So we have one. So we're going to have the biceps brachii. So we're going to assume that the biceps brachii produces a force FM1. Actually, let me draw the 3 muscles, and I'll draw the forces on the free body diagram. Next, on top of that, we're going to have the brachialis muscle. And so the brachialis muscle, something like this. I'm kind of exaggerating the distances a little bit just to make the problem a little bit easier to do. In reality, you don't have these kind of long attachment angles, but attachment distances, but you know, it's a little bit harder to do the problem otherwise. Okay, and then finally we have the brachioradialis, which we'll assume is acting. Okay, so we have three muscles here and the elbow joint. So let's go ahead and let's go ahead and state the problem statement. And so in this problem, we're interested in computing 3 muscle forces. Elbow joint reaction forces. Okay. All right, so let's start the same as we did last time. So let's go ahead and draw our free body diagram. And so, we're primarily interested in the lower arm. So I'm gonna go ahead and draw that. Just like before, we have a pin support or pin joint here at the left. Or forget, let me go ahead and draw the joint reaction forces. Okay. So let's draw all the muscle forces first. So let's draw the muscle force from the biceps brachii. So just like the first problem, we're going to assume that this is pointed vertically upwards. Okay. So that's a right angle there. This distance here is, we'll call it L1. Okay. Next, we have the muscle force from the brachialis muscle. And so, we'll say that it's approximately right there. We'll call that FM2. Unlike FM1, we're going to assume that FM2 here is pointed at an angle. Okay. And so we'll call this angle here theta 2. And we'll assume that FM2 acts at a distance of L2 away from the joint. Okay. Next, we have the weight of the arm. Okay, so we're going to assume the weight of the arm is somewhere right here. Okay. And just like just like the last problem, we're going to assume this moment arm is LA. Then we have the force from the brachioradialis muscle, and so that's going to be FM3. It's acting at an angle of theta 3, and its distance from the elbow joint is L3. Okay. And then finally, we haven't used yet. Yellow, I guess. And then finally, we have the weight of the object itself, W, and its respective moment arm, L. Okay. All right. And so all of the unknowns in this problem are FM1, FM2, FM3, RX, and RY. Okay. And so in total, we have 5 unknowns. And so to solve for those unknowns, we're going to need 5 equations. Right? That's just kind of algebraic, necessity. Right? And so, you probably might be thinking, like, hold up, wait a minute. If we do our equations of motion, we only get 3 equations, right? So we have some of the forces in the X direction, some of the forces in the Y direction. We sum up the moments around the elbow joint. That's only 3. And so, we don't have enough equations here to solve for all the unknowns. And so how can we solve this problem if we only have 3 equations of motion? So this is a very common problem in biomechanical analysis. And so, because you have so many muscles in the body, and they all kind of act on the same, on the surfaces, it's very common that you don't have enough, strict equations to solve for those unknowns. Okay. And so there's multiple ways that you can deal with this. And so, one way that we'll go over later in the class, I think maybe closer to Thanksgiving, is we can use what's called an optimization algorithm. Okay. And so I don't want to go over optimization just yet because it is a little bit intense. But that is kind of the industry standard way to kind of solve these kinds of problems. Okay. And so if you don't have enough equations, you just run it through an optimization, and then it can get you what you need. Okay. But what we can do right now is we can make some additional assumptions to generate some more equations. And so what kind of assumptions can we make? And so one assumption that's actually pretty reasonable, and so we have a lot of data that backs this up as a reasonable assumption, is we can say that the amount of force that the muscle can produce is proportional to its cross-sectional area. Okay? And so mathematically, this looks like this. And so we say that Fm is proportional to its area. Okay. And so what this means is that if we take the ratio of 2 muscle forces, so let's say the ratio between Fm1 and Fm2, this means that this is going to be equal to the ratio of the cross-sectional areas. Okay, so we have A1, where A1 is the cross-sectional area of muscle 1, and A2, which is the cross-sectional area of muscle 2. Okay. And we can make more relationships like this. And so we can say that Fm2 divided by Fm3 is equal to A2 over A3. Okay. And we can use even one more. So we can make the same equation for Fm1 and Fm3 as well. Okay. And so intuitively, this makes sense. And so it basically says if you have a bigger muscle, your muscle can produce more force, right? And so if you have a bigger muscle, that means you have more muscle fibers packed into that area. And so more muscle fibers means that you can produce more force. Okay? And measuring cross-sectional area is actually not that difficult. It is still a little bit annoying because the muscle is inside the body, but you can get pretty good estimates of cross-sectional area just from external measurements. Okay? And so you can do things like measuring the circumference of like your arm. And then based on that and based on some morphological data, you can estimate, you know, what's the cross-sectional area of like your biceps brachialis muscle. Okay. Right. And so this is pretty clutch here because now, you know, even with these two equations, if we supplement this with the 3 equations of motion, so we do F, sum of force in the X, sum of force in the Y, and some of the moments, then we have all the equations that we need to solve for these 3 muscle forces. Okay. All right, but we are out of time, and so we will do that next time. And so, are there any final questions today before we wrap it up? Okay, all right. And so on Tuesday, we'll pick up this example here. I'll kind of show you how that's done. And so we'll use these kind of area relationships to solve for the muscle forces. And we'll do maybe 1 or 2 more examples, and then we'll wrap it up from there. Okay. All right, so have a great weekend, everyone. Thank you, everyone, for tuning in. I'll see you next Tuesday if I'm alive. You know, after this weekend. I hope I will be. The groom said he doesn't intend to drink at all because he doesn't want to embarrass himself in front of his in-laws family. And so he said whenever people ask him to drink, then the groomsman is going to have to tank it for him. And so, you know, I might be drinking a lot. So we'll see. All right, have a great weekend, everyone. I'll see you next week.
Stay safe, Prof.